welcome to our February edition of ML4LM. And yeah, great pleasure to introduce Ewan, who's going to be talking to us a little bit about the work he's been doing at ECMWF. So a bit of a background, Ewan did his PhD at Reading University in data simulation. For the carbon cycle, he was working with a simplified land surface model and conducting field campaigns at the Alice Holt flux site. After that, he continued doing a postdoc at Reading as part of NCEO using the Joules land surface model and implemented the Lavender system, which is an ensemble variational data simulation system for parameter estimation. And has actually now become part of the Thamsat Alert Soil Moisture early warning system over Africa. So that's really, really great work. After his postdoc, he took a bit of a break working for a startup in London, but it was still doing climate research and using machine learning. So he's never gone too far from the field. And then he's joined ECMWF, where he now works with the AIFS and the AI-DOPT system with a focus still on land. So I'm really looking forward to this talk. Yeah, take it away, Ewan.
Yeah, thanks a lot, Nina. It's yeah, very kind introduction. Like Nina says, I'll be presenting a bit on the work we're doing at ECMWF, and in particular, sort of adding land variables to this sort of machine learning forecasting system that we now run, and then talk a bit more about this new work that we're doing, which we're calling direct observation prediction. As a kind of overview, I'll start out just looking at the kind of traditional weather forecasting workflow and how that looks, just so we have some context of where these machine learning models really sit, because then they're not really getting rid of the whole forecasting chain. They're still dependent very much on the traditional data assimilation system for their initial conditions and training. So we'll kind of look at that first, then see how these sort of AIFS, GraphCast, these different machine learning weather forecasting models have kind of come to rise up and be used quite a lot now everywhere, and what they're actually doing. And then we'll talk about how in the latest versions we've been adding these land surface variables to these models, and the different problems that we have when we're trying to add these new components to these models, because initially they were all run with just the weather components and the weather parameters, and now we're trying to add these different sort of Earth system components. We have different challenges there. So I'll talk a bit about the not just the successes, but also some of the issues we face as well to keep it balanced. And then I'll go on and talk about this more kind of exploratory work, should we say, that we're doing, where we're saying how can we do these type of models, the big machine learning models, just from observations alone. So no physics models or data assimilation products in there. So kind of just to give us a bit of an overview then of how these how we're currently making weather forecasts in the traditional system, both at ECMWF and most other operational centers. We're kind of every 6 to 12 hours, we're gathering all these hundreds of millions of observations from satellites, aircraft, radio sondes, surface stations, weather balloons, etc., etc. And we're combining that with our kind of physics models using the procedure of data assimilation, minimizing a cost function and finding what we deem to be the best estimate to the state of the atmosphere. So that state of the atmosphere gives us a really good initial condition to launch a physics-based forecasting model from. So it gives us kind of the temperatures, the pressures, the wind variables at that snapshot of time in the atmosphere, which we can then launch our kind of usually Fortran-based physical forecasting model from. We can then produce a 10, 15-day forecast, and then we have this process of post-processing and dissemination to users and people who want to know what the weather's going to be doing. So that's how it's looked for a long time. We're not only doing weather forecasts at ECMWF, we're involved in a lot of other activities. We're doing sort of climate monitoring, atmospheric monitoring, seasonal prediction, hydrology, lots of things. But one of the big tasks we do is produce and run backwards in time the data assimilation system to produce what we call a reanalysis. So that's kind of the state of the atmosphere for the the previous sort of 50 years or something. And our data set for that is error 5. It's available 1940 to present. It's a quarter degree. It gives us hourly estimates to the state of the atmosphere, and it's very big, 5 petabytes. So if we're thinking about machine learning is all about having big data. So this is a huge data set, which is obviously kind of ripe for training a machine learning model on. We're also now entering production soon on Error 6, but I don't know exactly when. I think these things get shunted back quite a lot. So just if we take a step back, I mean, I'm sure most of us are aware here if we're attending an LM for ML4LM, LM for ML1. But yeah, so machine learning isn't necessarily a new idea. And just to kind of highlight this, we've got a picture of this chap, Frank Rosenblatt, programming his single layer perceptron back in the 1970s. So the kind of mathematics and the ideas behind these techniques was there for a long time, but it's really the case that compute and data have got to a point nowadays that make these techniques very effective. So we had the kind of the development of GPUs, graphical processing units, and initially that was for kind of video gaming or for kind of 3D rendering of animations. And then someone realized actually all that mathematics is exactly the same linear algebra that we use for these matrix multiplications in machine learning and similarly in DA, really. So that was a very nice breakthrough on that side. And then obviously with the internet and digitization of all these records, we had a huge boom in the amount of data that we have around to be able to train these models too. So it was kind of a perfect storm, I suppose, in some ways that we then were able to do this stuff. And obviously, if we think about the domain of weather forecasting and more broadly kind of geosciences, the Error 5 dataset that we've just talked about there is a very clear resource where we can do some of this stuff with. And that's kind of what happened a bit in the sort of early 2020s, which we had sort of in 2022. This is kind of the timeline of when we started seeing these machine learning based weather forecasting models. And in sort of early, there was a few different things that happened before this, but I'd say the first paper that's quite a nice paper to read if you have an interest or don't have an awareness already. This guy Ryan Keisler wrote this paper where he was using what's called a graph neural network trained on Error 5 to predict the forecast, and he showed like a quite nice level of skill doing that. And from this paper onwards, then there was a bit of an explosion of all these different places doing a similar thing with different architectures of machine learning models. So we had sort of GraphCast from DeepMind, we had Pangu Weather from Huawei, we had a Microsoft version, we had NVIDIA doing this kind of forecast net, and then more recently we've had from ECMWF in sort of 2023 around about, we had the AIFS, so the Artificial Intelligence Forecasting System. So similar to the integrated forecasting system, we have the IFS is the traditional system at ECMWF. We now have the AIFS. And so if we look at the traditional forecasting system chain again, really all these sort of forecast models, these machine learning forecast models are replacing is this part here. So really, it's still very similar. They're trained on data assimilation products and they're initialized from data assimilation products. So they're kind of completely dependent on still the kind of data assimilation system that is running. So that's nice. It means that if we are involved in data assimilation or modeling or whatever else, we're still the kind of machines aren't coming for us yet. But so the nice thing about these models is obviously they're very fast to run, and they can minimize the errors in the forecast model because they're trained on these data assimilation products, which we know are very accurate because they're combining the kind of best of both worlds of observations and physical models. So when you train a model on this product, you're able to minimize the errors in kind of traditional forecast models. And our particular forecast model, the AIFS, looks a bit like this. So this is basically it's an encoder processor decoder architecture, which means essentially what we do is we take the full atmospheric state and we compress it down to a lower spatial resolution. So we go from the Error 5 resolution, which is about 30 kilometers, and we compress that down to a 1 degree grid, so about 100 kilometers. And then in that 1 degree grid, that compressed space, we update in time. So that's where we do our kind of update 6 hourlies in time, and then we have a decoder which pops back out to the kind of 30-kilometer resolution once we've done that update in time. So what happens here is we're giving the model two error 5 states, and we're asking it to predict the error 5 state 6 hours in the future. So at the moment, that's the resolution in time of these models. So they're 6 hourly. So you give it 6 hour slice, and it predicts the next 6 hour slice. And in that way, you can build up this kind of auto-regressive forecast. You just keep cycling the predictions back into the model, and then you can build up a kind of a 10-day forecast into the future. I should say the kind of the backbone that is doing all of this work is exactly the same kind of machine learning model that is used by all these big LLMs, ChatGPT or Claude or whatever else you might like to use. It's this transformer which has this notion of attention. And this means that once we've compressed the atmospheric state down to this 1 degree grid, the transformer can have attention across latitudinal bands. And rather than saying, okay, here's the context of the previous N words, give me the prediction of the next word, which is how these large language models work, we're kind of saying, here's the context of the atmospheric state. You can pay attention to this and give me the next atmospheric state. Instead of saying, here's the previous N words, give me the next word, if you see what I mean. Is a loose analogy, I would say. So there's nice things that come with this. So like I say, we this is showing you this kind of very traditional plot that we have in weather prediction, where we show the kind of the improvement in skill. This is anomaly correlation for Z500 geopotential height at 500 hectopascals, and the increase over time. And this is through improvements in modeling, improvements in data assimilation techniques, and kind of inclusion of new and novel observations. And we see that from 2006 to 2024, we have a really nice improvement in skill in different lead times of the forecast. So day 3 to day 10. And then these little bits at the side here, this is now the AIFS. So you can see that this is quite a significant jump in skill for Z500 in particular, but for many variables. And like I said, this mainly comes from the fact that we're learning to emulate this analysis product. So this analysis product's very skillful. So rather than trying to predict forward in time, emulating a traditional forecast model, we're emulating these data assimilation outputs, which means that the forecast necessarily can be minimizing some of these errors. We also see nice case studies, so it's not just like these big scores that it's able to kind of gamify and minimize. This was one of the first examples we saw at the start when we operationalized this AIFS model that we trained. There was this kind of very rare snow event that happened over sort of Florida and the Gulf of New Mexico. And you can see this was what actually happened, the verifying kind of short range forecast or analysis. And we caught that in the forecast for the AIFS at day 10, whereas we didn't have that in the IFS. But I mean, the IFS still probably has nicer structure, it's a higher resolution, but you can see that this system's able to capture what was going to happen there quite well in a way. So this was a very nice kind of use case to show that the system is doing something physical. And this in particular was nice because there's not really a very close analogy to this in the error 5 dataset, which we trained on. So it means really, well, we hope it means that the model has learned a kind of a consistent representation of atmospheric physics within its kind of latent state, as it were. So that's yeah, it's nice to see these kind of examples to really kind of bring that to the fore. Like I say, the other nice thing about these models is that they're very cheap to run, but I mean that's with the big caveat that they're not necessarily cheap to train. So once you've trained your model, you can run it very quickly. This is kind of showing you a bit of a tongue-in-cheek comparison of how many computing units it took to, which is normalized amount of time and amount of processors. It took to produce error 5. So this was 15 billion to run one high-res ECMWF forecast with the traditional model. It's about 180,000, and to run one AIFS forecast, it's 0.3. It's this little ant fella down the bottom. But like I say, that's kind of putting a curtain up across how much it costs to train these things. But nowadays, actually, the training cost for the AIFS has come down a lot. So to train the full model, we can train it over about 3 days, and that's across about 16 nodes, each with 4 GPUs. So that's 64 GPUs or something. So yeah, it's not insignificant, but it's no longer that we're waiting weeks and weeks to train these things on hundreds of thousands of GPUs. It's a lot lower, and I think that will come down again as we figure out better ways to do this. So yeah, it's a constantly moving number, the amount of time it takes to train these things, I would say. So right now, let's get to the point where we're actually going to talk about it. So that's kind of the context of what the AIFS is and what it's doing, hopefully to a certain degree. Um, and people do, yeah. If anyone does have questions or anything, feel free to put in the chat, or I don't know if you can raise hands or anything during, but afterwards, I'm happy to answer questions obviously as well. So this is what we were doing in preparation for the first operational release. So we had kind of run the AIFS in some different guises in what we call pre-operations, which meant that it's not really supported by forecasters 24/7. We were going to train an operational release of the AIFS, and it was decided that when we did that, we wanted to include some new variables which users had kind of requested. So these were variables around both the land and things that are sort of pertinent to the energy sector. So that's things like 100-meter winds and solar radiation for energy modeling. And on the land side, we were adding in soil moisture and soil temperature. So you've got a kind of a snapshot of what the forecast looks like here for soil temperature in the top right hand plot and soil moisture in the bottom right hand plot. We were also adding cloud covers and snowfall and runoff to gain some kind of notion of hydrology as well. So you can see here, this is surface solar radiation on the left and cloud cover on the right. It's a bit smooth. It's a bit the quality of this figure is not too great. But the nice thing is that you can see there's an internal consistency in the model between both the solar radiation and the cloud cover. So you can see that the surface solar radiation is lower where we have cloud, as you'd expect. It intercepts the radiation, so you have lower solar radiation at the surface where in places where you have cloud. So clearly the model has developed a kind of a consistent physical representation of cloud, and this is true for other variables as well. And we'll talk about some cases where maybe it's not necessarily done that in a very good way in a minute. But so just to kind of give you a very brief context for how the development procedure of this things looks like. So we're training all of these now in an open source project called Anemoy. So this is anyone can go and grab the code base here. It's under this github.com ECMWF Anemoy core. And lots of people are now training models using this code base, and it's like I say, completely open source. None of it's proprietary or behind a wall or anything. So I think that's been a really nice thing, because I think the thing is with these things, there's so many different options that you can do. So if more people can be developing this and more people can test things out, then it really helps to kind of understand where the science is going, because I think there's too many questions to ask from one center or one tech company alone. So that's good. But yeah, so what we do basically is we train the model on the Error 5 data set from 1979 to 2022, and we go through many epochs of that. And then once the model's kind of converged there, we train what's called a rollout. So we train the model to be able to forecast 3 days into the future. So we only train it for 3 days into the future, and then we run 10-day forecasts. But we fine tune on this AIFS operational analysis, because when we initialize it in real time, we'll initialize from the AIFS operational analysis. So we kind of had to get the weights to get accustomed to what the AIFS operational analysis looks like, because obviously it's a bit different from Error 5, because Error 5 is a few model cycles old now. The AIFS operational analysis is kind of a few model cycles in the future. So we fine tune on that to get the model accustomed to what the kind of initial conditions will look like that it's being started from. But basically that's how it looks. And so in theory, it should all be okay. And what we did when we were doing this first operational release, we did all this big long training on Error 5. Everything looked good, and then we fine-tuned to AIFS operations, and what we got out was this. And just so for context, I'll talk you through what this is on the left-hand side. So this is a scorecard for our for our weather forecasts at ECMWF. So what we do is usually we run a load of forecasts for a set period, and then we produce a scorecard where red means that the model is worse than whatever you're comparing to, and blue means it's better. And what we have is different sections for like geopotential height. We have temperature at different levels in the atmosphere. We have wind at different levels in the atmosphere for different regions. So northern hemisphere, southern hemisphere, and tropics. And what you can see here is after we've done this fine tuning to IFS operations, that this was compared to the previous AIFS model without land variables in it. The everything was worse. Well, not everything, but most things were worse. And so, oh no, we've done all this training. It's taken us so long, and we've just produced a duff model. And then what we realized was actually the main difference between these two versions of the model was including the land. And the main difference that we realize as well between error 5 and the more recent IFS operational cycles is that the land surface characterization has completely changed. So we have vegetation types have changed. We have different areas of vegetation cover where there wasn't before. All these type of things have changed from error 5 to a more recent operational cycle. And so when we're training these machine learning models, what we do in the first stage, we have this what we call a learning rate. So it's very similar to minimizing the data assimilation cost function or any cost function. You have a gradient descent, and you make what you call like a step size, and you decrease the step size each time you make a step so that you can force convergence of your minimization problem. And we have that in machine learning too. I mean, I'm sure many people are aware. You have this thing called a learning rate, which is basically controlling how big a step you can make in parameter space each time you kind of are trying to minimize and kind of converge the weights of these big machine learning models. And so what we had really done with training on error 5 and then fine tuning to operations, we keep a very, very low learning rate or step size when we do this fine tuning. And so that meant that we were basically in and around this local minima of the error 5 land conditions, and we couldn't jump out of that. And so what we actually ended up doing, and this was a nice idea from Anna Prieto Mezio, who it was me, Anna, and Gabrielle Moldovan who were training this first operational release. She thought, well, what we could do is we could increase the learning rate when we go to this new data set, just to allow it to jump out of this local minima and try and find a better solution. So that's what we did. We basically, in the fine tuning to IFS operations, we kind of increased this learning rate, allowed it to just explore the parameter space just a bit more. And then we ended up with this scorecard compared to the previous version of the model. So we've got now the new land variables in there, and we've got a nicer scorecard. So this scorecard's quite blue. That means that it's basically that these variables should be displaying more skill at like day 5, day 10 into the forecast. So we were very happy with that. It was all good. And so this is just for context. This is what the scorecards look like. This is the first one we had that was rubbish, the one we ended up with, and this is the candidate that we have compared to the IFS, the traditional system. And you can see there's lots of blue here, but there's the one exception is really high in the atmosphere. So at 50 hectopascals, because what we do in the model, we say, I don't care about the top of the atmosphere, no one lives there. So we downweight that, and that means that the model doesn't do as well there. It kind of almost uses it as this store of strange value that it does weird things with. But we can talk more about that later if people are interested. But yeah, so just to say, yeah, we're not doing better in the very high atmosphere, but otherwise we're kind of consistently outperforming the traditional system with this model. So that then went into operations. We've also got now an ensemble machine learning forecast system, AIFS Ensemble, that was operational as of June 2025. And so if you go on ECMWF charts, you can look at all the forecasts from these models, and we were seeing very nice initial performance. But just again, for a bit of balance, I mean, this is the first time we'd ever put one of these things into operations, right? So it's naturally the case that we don't know what we're doing. So when we first put this in operation, everything looks good. Oh, the scores are still good. Everything's going along well. And then what happened was we had what the forecasters started to refer to as rainpox. So you can see here the the AIFS basically started to develop these very small blobs of unphysical rainfall in locations that were far away from any kind of big large scale systems or anything like this. So you can see that here. There's this like little dimpling of blobs of rain, which really are very unphysical. And so and then it was like, oh no, we thought we'd done everything well. We've got these rain pox, and I mean, it's again, it's really kind of trying to understand what these models are doing and where these kind of where the limitations, what are good, what are bad, etc. And what we found when we started investigating this was really interesting. So um, there was a couple of causes for what we called the rain pox, and part of that was that we started a new operational cycle at ECMWF. So we were initializing the model now from initial conditions it hadn't seen because there was a new version of the IFS. Um, and oh, I think is there a question? Oh, yes, good question. What does a model being operational actually mean compared to just say open source code being available on GitHub? So it's a good point, and it's quite an ECMWF centric word, I think. So, I mean, in terms of ECMWF, an operational model means that it's supported 24/7 by the forecasters. So if it ever falls over, someone is on call all through the night to get it back and running. And it means that the kind of pipelines for how it's disseminated and pushed to the member states and other people who contribute into ECMWF is slightly different. So that's basically the main part of it. But it also means that then it's got more visibility and it's being used more by the forecasters and it's routinely being checked and run and is there with a certain agreed upon latency that people can then grab it. So that's kind of the main thing. But yeah, it's a bit of a nebulous word, I suppose. But so to go back to the rainpox, basically we had this new updated cycle at the IF. So we had a new version of the IFS, new data assimilation. And what actually happened was the soil moisture conditions in this data assimilation product that we were now initializing this machine learning model from were quite different. So we'd implemented something new in the DA, which had actually broken things a bit. And actually that was me who had done that. So so I'd kind of broken the system in some way, which meant that we ended up with these very wet blobs of soil moisture in random locations. And we it was very nice. There was a couple of people in my team, like Christoph, Pete, others who were tracked down this issue, and then we figured out a fix. We fixed the IFS, and that also helped the rainbox. But the other thing, so these very wet blobs of soil moisture, which were in isolated conditions, basically triggered the machine learning model that had learned that it was never seen this before. And it said, "Oh, I've got a very wet blob of soil moisture, but I've got no rain above it. That doesn't seem right. I'm going to put a blob of rain above it because there must be some rain here to drive this kind of wet soil." And that's obviously the wrong physical mechanism. I mean, we don't want wet blob of soil to make rain. Well, I mean, it can do at longer lead times, but initially you don't have that in the 6 hour kind of range. So what we had to do is we also had to retrain the model because the model had learned this unphysical relationship between soil moisture and rain that at certain conditions it could, if you had the right soil moisture condition, just put a bit of rain there just to think, well, that's probably going to make the scores better. So we retrained the model and we downweighted soil moisture a lot in the loss. And this actually stabilized things a lot and meant that it no longer produced these kind of physical blobs of rain. So now we had this forecast field, whereas before we had this, it now looks like this. So it looks much more physical and much more reasonable. And this encouraged that kind of the correct dominant relationship between those two variables rather than what we had before. But it's just quite a nice example because it shows that these systems aren't necessarily just about throwing all the data at the wall and giving up on physical modeling. They still require quite a lot of insight, both physically and statistically, to understand what's going on and try and encourage the right behavior. So you have to bake a lot of strong inductive biases into these systems, which, I mean, it's the same with physical models, right? When we code up a physical model, we bake in a lot of sort of biases or things that we think might be the case, but especially when we get down to the level of the land surface, there's lots of parameterizations, these type of things. So yeah, there's close analogies, I feel. So it's yeah, like I say, I don't think it's giving up on physical modeling at all. I think there's still a lot of that intuition that will be necessary. And we're still training on products which are coming from physical systems. So yeah, so that was kind of a bit of an insight there, just to kind of summarize on the AIFS front, what's coming up next. So like I say, you've got these we've got these charts now available that you can go and look at and everything. And if people are interested, they can go and try this out themselves with the Anemoy code base. And there's some model weights and things on Hugging Face, which is a kind of a website for sharing machine learning models. And the next steps really, we're adding more variables. So with Nina and others, we've been working to start putting snow in for the next version of the AIFS. We don't have snow depth in there. We put in snowfall last time, but we haven't got snow depth yet. So that's starting to look good. Going to higher resolutions, more collaboration. So we're taking lots and lots of code kind of pull requests and contributions from lots of collaborators into Anemoy, which is great. So hopefully we can keep that going forward, because I think it really helps improve things. And then finally, we're starting to think about observations. At the moment, we've trained everything on these reanalysis product, Error 5, but can we push that forward and go somewhere else? So with that in mind, if we go back to this kind of workflow for building a weather forecast, we had just replaced this box here with a machine learning model. What we're saying next is, could we potentially actually just do this? So could we just train the model with only obs, and then could we see if we can predict the weather? Okay, I guess is the question. Okay, so we've got another question. Can you somehow add a physical term in the loss function to overcome that the model learns the reverse relationship between soil moisture and precipitation instead of down weighting the soil moisture in loss? So yeah, it's a really good idea, and I think we'll see more and more of these kind of what we might call physical constraints on the model. Actually, one of the nice things that we did in the first operational release there is we added some physical bounds on some of the kind of variables that were bound. So in the previous version of the AIFS, before we went operational, that we had like things like negative rainfall would come out of the model because there was no bounding on rain. So what we added to it this time, this was kind of work from Gabrielle, was bounding on precipitation, on humidity, and cloud cover, other things, to kind of give it a very strong prior of like cloud cover can't go below 0 or above 1. It's a value that's 0 and 1. Humidity can't go below 0. Same with rain. It's these type of things, and that really actually helped and improved the skill. So I think baking in some more of these kind of things does help, and probably we'll see more of that and more research into that going forward. I would imagine. Yeah, so going back to this, yeah, can we go straight from observations, train a model, just the raw, noisy observations, and produce a forecast? And so that's what we're asking with this AI the direct observation prediction, or AI DOP for short. So we train this kind of neural network on all these historical observations, and then we try and make it predict future observations. So whereas before we were giving it 6 hours of error 5, asking it to predict 6 hours into the future error 5. LLMs are saying, here's the previous word, predict the next word. We're now saying, here's the previous 12 hours of observations, predict the next 12 hours of observations, is the loose kind of setup of the problem, as it were. And we can include observations of the full Earth system here. So we're no longer thinking in components and saying, okay, well, we have to have an atmosphere model coupled to a land model, coupled to an ocean model. We're saying, just put in all the observations and see what it does is really the kind of the mantra, I guess. And this has the potential to give us a very, very quick ability to forecast. Because at the moment, when we have all those observations coming in, we combine it in the data assimilation procedure. That takes quite a lot of time. That's maybe an hour, something like this. And then to launch the forecast model from that, we have to wait a bit more time. Then the forecast model takes maybe about half an hour to an hour. So there's a long chain waiting for all this modeling and data assimilation and stuff to happen. Whereas the like I say, the thing with these models is they're super quick once they've been trained. So if you have your observations coming in real time, and you can just launch your model directly from them and produce a skillful forecast, you can potentially give out kind of faster access to warnings and yeah, sort of people have quicker access to the forecast and these type of things. So this is what the model looks like, and there's a nice paper from Mihai kind of documenting what the model is like and what it's doing a bit more in this paper. And now, I mean, it's a very similar thing to the AIFS in many ways. But now, instead of having just an error 5 state and an error 5 state on either side, we have loads of different what we call encoders, which kind of are a way to condense that information down into this latent space that they call it, this reduced resolution kind of baked space in the middle. And that allows us to kind of encode satellite observations, conventional observations from aircraft, synops, whatever else we might have. And then we bake that down into this latent space, and then we still have this transformer backbone that had this notion of attention across report types and across space. And then we decode back out to these observations. So like I say, we're giving it 12 hours of observations in the past and predicting 12 hours into the future. And then you calculate the loss against those observations in the future, which it hasn't seen. And then you do that many, many, many times, train it for epochs, and you get a model at the end. And this is just showing you the sort of thing that looks like. So on the left-hand side, we have the real observations from the geostationary satellite Saviri. And on the right-hand side, we have the free running model predictions of the same thing. And the nice thing here is you can see like it predicts these kind of weather systems and stuff that are coming through very well. I mean, it's a bit blurry here. It's trained against a mean squared error loss at the moment, this one. And that kind of sometimes it makes a bit of blurring because it's trying to minimize the errors and kind of reduce the double penalty and these type of things. But you're getting this nice convection over Africa and stuff as well. So it's learned a very good representation. But you might say, why do we care? I mean, who cares if you can predict Saviri Channel 3 at 3 days into the future? I want to know if it's going to rain or if I could go to the beach. So the nice thing about it as well is it learns a very, very good relationship against the kind of what you might call anchor observations or conventional observations, and it can fill in the gaps very, very well. So once it's got the ability to kind of produce a good forecast of all these satellite radiances into the future, if you have a good sort of ground truth observational network of some of these things, it can interpolate in space very, very well. It's not just doing a smoothing in space, it's learning kind of an observation operator, as it were. So it's learning when the brightness temperature from these different satellites looks like this, I know that the 2 meter temperature looks like this. So it's kind of learning all of these relationships at once, and you're training it end to end. And I think there'll be many ways that we can refine this and do this and again maybe introduce more kind of notions of physical constraints and these type of things in here as well. But you can see in this example, what we're showing you is the input wind observations from the SYNOP network that we have for about 12 hours. And you can see they're very sparse. We have very, very few observations over Africa or in the southern hemisphere and polar regions. But then once we make these predictions and we have all the complementary satellite observations, the model's able to produce a full field of winds that looks very, very physical and quite similar to what we'd get from the IFS, the traditional sort of forecasting and data simulation system at ECMWF. So it's very good at filling these gaps and learning these relationships. And so just to kind of give you a look at how the scores are looking, we've actually had some more recent updates to this now, but I mean I haven't put it in. But the main idea here is this is the kind of progress in the models that we train. So this is a model we trained in May 2025. This is one that we trained in June 2025, and this was one that was trained in August. And what we're showing you here is the forecast error of temperature at 850 hectopascals in the atmosphere, and this is from day 1 to day 10. So you can see the error grows as you go through the forecast. Obviously, we get further away from the initial conditions, and the error in the forecast grows from sort of 1 to about 4 or 5 Kelvin. And so you can see initially the blue line is the IFS and the pink line is this AI DOP system. Initially, we're quite far away from this. The model that we trained in June was getting closer, and then by August, we're kind of getting very close now to what the skill of the IFS is, and you can see at sort of the short lead times, we're almost getting ahead of it. So it's looking okay, but I mean it's very fast evolving, I would say as well. I mean it's just there's stuff going on all the time, so it's very exciting though. But it's lots of different things to consider and different observations to use and etc. etc. So I think that's pretty much where I'll leave it for now. So just to kind of wrap up, I mean, we are definitely seeing kind of an increasing emphasis on using machine learning at ECMWF for weather forecasting, and I think that will now be the case going into the future for sure. We've got our first, like I say, operational, so kind of run with certain conditions attached to it in the AIFS single and the AIFS ensemble models. And we're starting to expand to other Earth system components now. So we included these land components, but Nina and others at ECMWF are working to expand this even further as well. So we're constantly pushing both in the ocean and the land to add more variables to these models as well. And now we're starting to think about how we can use observations more directly in some of these models, and if that will actually be useful in the future. So I think this is still very much an open question. I don't think anyone's making any big decisions on this yet, but I think it's a case that we feel like it's something we need to explore to make sure and understand what the limits are for predictability when we look at these type of systems in this context. So yeah, thanks a lot for listening to me there ramble on for the last 45 minutes or whatever it was. And yeah, happy to answer any more questions that people might have about any of this.
Great, thank you, and that was really fantastic. Yeah, please, any questions? Please put them in the chat, and then Ewan can ask them. I guess while we wait for questions, I'll ask you the slightly mean one of what does this mean for the future of physical modeling and or Aero5 if we're moving towards these kind of dot systems?
Yeah. No, I think yeah, it's a very good question. I mean, I think I think for me the physical system will remain key for quite a long time. Yeah, I think it's very important to have, I mean, there's so much trust baked into these traditional systems that I don't think you can just say, oh, we're going to get rid of it. You know, you need a baseline to really understand what these things are doing and have some sort of judgment to make against it. And I think with the physical system, we've had decades of understanding how to do that. And I don't think we can attribute the same kind of respect or kind of trust it in these new systems until we've really run them for longer. So I think eventually maybe things do change, but I think for now I see that the physical system's still very key. And I mean, even if nothing else, right, we're using it still for training data and initialization of the AIFS. So but yeah, I think it's a really good question, and I think it's something that's going to be asked more and more, right, going forward. And it's very hard to know exactly what balance you take when you're. I mean, for people who are making these decisions on where the resources go for development, I wouldn't like to have to make those decisions.
Great, I think there's a few questions in the chat. Are you happy to read them
Yeah.
out?
Oh yeah, sure. Okay, sure. Well, thank you very much for the first one. It's a very, it's very nice of you to say that you enjoyed the presentation. I'm glad that I wasn't rambling too much. Um, So yeah, next is Andrew. Oh yeah, thanks for the question, Andrew. So can you speak to how direct use of observations relates to land variables, given the limited number / type of observations relative to those of the atmosphere? And I think this is a really good question, and it's something that I've kind of been thinking about quite a bit, and as well with Nina as well. And I think it's really tough because you're right. I mean, when you think about the number of soil moisture probes we have, or the number of flux sites compared to what we have for, I don't know, 2 meter temperature, or it's very sparse. But then equally, it's not too dissimilar to what we have for sort of radiosondes, and we see very good generalization when we just train with the radiosondes as the upper air, and it produces the atmospheric fields which are very good. But that's also not to say that we don't have a lot of satellites which are trying to observe directly the atmospheric layers of temperature which the radiosondes are kind of tied to. So I think it's going to be tough, and I think when we start going down that route, what we might end up having to do is looking at very trusted level two products or things if there's stuff that we really think that we want a notion of in the model. I mean, it is there in these satellite observations, but it's whether or not you're happy with it just being a radiance, or if you want it somehow to be converted to something that we have more understanding of, like soil moisture or carbon flux or whatever else it might be. Um, so I think yeah, it's definitely an open question, and I think maybe some notion of physical modeling comes into that chain somewhere because you say I trust this retrieval, and let's use that retrieval to train the model against to be able to predict the the variable that we're kind of more interested in. But I think it's very fresh, so I don't have a good answer for you. I'm sorry. And then yeah, so then we have Jarmo who's saying, how far have you pushed the forecasting part? Talking with Matt previously, the AIFS should be sort of stable up to a year. Yes, yeah. So in terms of how far can we run the model into the future before it kind of falls over and it diverges? So it's a good question, and the models are all almost kind of overfitted, as it were, to medium range forecast prediction because that's the task that we're trying to do with them. And that has meant that I would say the older models that we were training definitely weren't stable past a few months. You'd run it for a few months and it would quickly diverge, and you'd see this, I don't know, this kind of saturation as everything got very warm and the planet turned into a big hot sun. But now I would say, yeah, Matt's probably not too far off. And we've also now started training with other people these kind of there's some nice examples. There's like ACE2 and stuff. There's these climate emulators which do a very good job of having stable dynamics at sort of like 20, 30, 50 years into the future. And I think that's very possible with sort of residual connections and doing different clever things with the model to make sure that it maintains stability into the future. I think that's an active topic of understanding how much we want to enforce stability versus how much we want to kind of run after like medium range skill, and that's a question for I guess depends on your aims. But yeah. Next is Rolf. Thanks for a great presentation. No problem. You're welcome. You showed scorecards improving with the inclusion of land variables. These improvements were strong, quite high up in the atmosphere. Yes. Was there something else different between the X and control besides the land? I hadn't expected such strong impact from the land. Yes, no, and it's fair to say that it's not all coming from the land for sure. It's quite a lot of that will be coming from some of the other updates that we made in the operational release. So these are things that I kind of touched on briefly. So this bounding from Gabrielle made the model behave quite a lot more physically in terms of humidity and precipitation and some of those variables, which meant that you didn't necessarily see some of the kind of like we were saying with the climate emulation as well. You didn't see some of the collapse in some of those variables at longer lead time. So the skill was improved there. The land surface definitely did help, but it was only a fraction of those blues. But the training regime as well, we slightly updated, which allowed us to kind of like this kind of kicking up of the learning rate, allowed us to get better accustomed with the operational conditions that we were initializing from. So that was very beneficial as well, I think. But the land was in the mix and it did help. But you're right to say that that probably wasn't the cause for the kind of winds at 250 hectopascal big improvement. So yeah, I think that's very fair. From Pierre, can you talk about the current work on merging DA and AI forecasts at ECMWF? It seems that there are still issues, spurious correlations and gradients with AI forecast systems. Yeah, so I guess Pierre, you're getting at the kind of idea here that you could, with these trained models of the atmosphere, you could then use those in place of the traditional forecast models at the heart of your data assimilation scheme. And the nice thing about that idea is that obviously with these machine learned forecasting models, because all of the languages that you're training these models in are all automatically differentiable by default. So you can just take your model and do dot grad and you get the kind of the derivative of your model and therefore the tangent linear and the adjoint. But you're right to say that realistically, because of the way that these models are trained, they don't necessarily exhibit the right sensitivities when you do that to be very useful in a DA scheme. So I think that's probably partly why we started exploring this idea of direct observation prediction and training directly on the observations themselves, rather than going more down this route, as you say, this kind of surrogate adjoint with a machine learning model within the DA. And I think the other issue is, I mean, to try and interface these models within the current DA systems is tough from a technical standpoint. I mean, our current DA system is kind of part Fortran, part C. It's got kind of lots of different things going on, and then to try and interface in there a machine learning adjoint is quite difficult. So I think that people maybe didn't also have the will for pursuing that in depth. But I think you're exactly right as well, that the kind of sensitivities of the models maybe aren't exactly what we'd need for such a system anyway. And I think that there's maybe a caveat there that you could train a model that had the right sensitivities, but I don't know that people have really done that yet, or I'm not aware of it. It's possible there is literature around that, but yeah. The next one, anonymous, the soil moisture boosting rain case is a really good example. Yeah, no, thanks. I thought so. Yeah, that area could have an extensive area of wetlands, and the soil moisture may be wetted from below, not necessarily comes from precipitation. Yeah, good point. Adding physical constraints could be a good way, as mentioned, and may also be a good idea to add groundwater in addition to soil moisture in the training as well. Make the land goes deeper. Yeah, no, I think it's a good idea. I mean, so in this one, we also only included the top two layers of soil moisture because those are the ones that we really operate on in the land DA at ECMWF. So I think going deeper in the soil column and giving it some store of value lower down will probably be beneficial for the model for sure. I mean, I think what we do see is that these models almost develop like a latent representation of some of these systems, some of these processes anyway. So, I mean, with the ocean in particular and sea ice, we see that kind of already appearing, even though we haven't put it in. So, I mean, if we look at this plot, sorry, it took me a while to get there. This is soil temperature. So the model has no notion of sea surface temperature or sea ice, but it's got soil temperature and it's producing what it thinks is soil temperature around here. But you can see it's kind of also correlated with what might be sort of motion of the ocean and ice and stuff like this. So it's so yeah, there is some weird latent representations that the model starts building itself as well. So how much we can take that, I don't know. But so the next question, do you think there's any explainable machine learning techniques that might identify future rainpoxes? Yeah, I do, and there's a few people working on this at ECMWF, trying to understand the explainability of these models a bit more, and I think it's very useful work indeed. And you can, because you have access, like we're talking, to the gradient of the model sort of explicitly, you can very quickly produce some like sensitivity metrics which show you what the model is using to predict what and what is sensitive to what. So using that, you can then ask some of these questions and try and understand why is the model using soil moisture to predict rain or otherwise. And I think, yeah, trying to do that more will be very useful. In particular, with the DOP system as well. One of our colleagues, Patrick, he's been working on implementing an FSOI technique. So this is forecast sensitivity observation impact, which is what we use in data assimilation already anyway with the adjoint that we have there. But he's done that for DOP, and you see very nice kind of patterns in which observations it's using to inform which variables. So you see sort of stuff like ATMS is a predictor of kind of atmospheric temperature, and channel 6, for instance, is very sensitive to deep layers of temperature in the atmosphere. And you can see that the model is using that to predict, for instance, temperature at 850 hectopascal. So it gives you a bit of confidence that there's a physical mechanism it's learned that is reasonable. And like you say, hopefully then you can also start understanding places where it's not done that and try and guard against that for sure. Liz, yeah. Yeah, thanks. Do you think there might be ways to transfer the learned observation operators from the direct obs model back into data assimilation methods? Yeah, I know it's a good idea. I think I think you definitely could. I think you may want to set up the model in a slightly different way because at the moment like I say, it's hard to kind of interpret exactly what's going on in there. It's almost a bit of a soup. But if you had the encoders and decoders set up in a way that were easier to break out as single model layers. So the way that these things are set up, you have like lots and lots of layers to your model. You can have like like a multi-layer perceptron, which is just like linear weights with some biases in it. You can have then a transformer block. Then you have some layer norms and different things like this. And you can just then, if you've set it up in the right way, you could just split out a couple of those blocks and say, okay, let's just use those, and it's learned the representation between whatever radiance it might be in soil moisture or something like this. So yeah, I think there probably would be a way, but I think you'd want to, yeah, like I say, code up the model slightly differently to be able to do that in a decent way. So yeah, yeah. Thanks for the compliment. I'm curious, how does AIFS compare to previous systems in terms of processing speed? Also, oh, I missed the last bit. But how does it compare with processing speed? I can answer. It's yeah, it's super quick. I mean, it's like so to the IFS, like I say, to produce a forecast, 10-day forecast from the IFS is around half an hour to an hour. To produce it for the AIFS is probably a minute, less than a minute. I mean, and there's a caveat there again. I mean the operational model is 9 kilometer resolution. The AIFS is 30 kilometer resolution. The IFS is running with a kind of 15-minute time step. The AIFS is running with a 6 hour time step. So there's a big saving already there. But then also we're running on a single GPU, the AIFS, whereas the IFS is running on, I think, across like 32 nodes with goodness knows how many processors. So it's not linear comparison, but there's no doubt that these are very, very fast approximations of what the full systems are doing. So yeah, they're super quick. I mean, it's and in terms of now we have the AIFS ensemble model, and you can run a full ensemble with that in again less than a few minutes. So it's yeah, it's but like I say, the caveat again is that the training costs aren't negligible. That the cost is hidden behind all of that, which is allowing you to train the model to very, very well condense all that information into then just a very, very good approximator. And I think that's where machine learning is very good. It's kind of condensing of information.
I think you and we've come to the hour, so I don't know if you
Okay.
want to keep going or maybe we.
I'm happy to answer them, but how many is there left? Three?
There's,
I'll try and be quick. Shall
there's
I?
two questions left. Yeah, go on.
Yeah, okay, cool. So are there currently big efforts? Sorry, I was blabbering on there to those questions. I should have been more concise.
No, no, it's been great. It's been great.
Okay, well, thanks. Are there currently big efforts at ECMWF to improve process understanding using ML and observations and plugging new learned parameterizations back into the fixed model? I think there is some work to try and kind of make this a bit more of a life cycle, and I mean we are talking to each other a lot as well, so I think that will naturally come more and more. And there's also some work nudging the physical model towards the machine learning model done by Ina, which is very good. So yeah, so that's good. And then finally, just wonder when land variables are added in AIFS, does it improve the forecast skill for short term or in fact more long term forecast skill? How do you train the ML model to learn land atmosphere feedback properly? Is current AI architecture sufficient for learning such feedbacks? Yeah, I'll try and be brief, but so the we don't see it exactly as we'd expect from a physical model, where you'd expect the kind of longer term prediction to matter more when you had the land atmosphere coupling. It's slightly more nonlinear than that, but I would say that there's probably an element of that, but it's less exaggerated than we see with the physical models. And I think there's a lot of questions around how we do this architecturally going forward, and we're looking at other things where we maybe couple two models a bit more like a physics sort of system, and Nina's doing looking a bit at that as well as Lorenzo with these kind of ocean atmosphere coupling as well. So I think it'd be really interesting to see that develop more and see what the kind of comparison of those different types of train models looks like. But yeah, thanks so much for the questions, everyone. That was really interesting questions to think
Yeah,
about.
great. Thanks. Yeah, I know we went over slightly, but it's been great to actually have so much interaction. So please attend the next one as well. The next one's going to be in March. We've got Sung Min giving a talk on machine learning for hydrology benchmarking. I think that's going to be great. And then the other housekeeping note is that there's also the Pangloss meeting that's going to be happening in Stuttgart in July. And if you're interested, the abstract submission is at the end of the month. So I encourage you to submit message to that. But as always, this has been recorded online. So if you've enjoyed it, share it with your colleagues. All the past ones have also been registered, recorded, so you can watch past ones. And yeah, please join us next month for our next one. Thank you very much.
Yeah.
Bye, everyone.
Yeah. Thanks a lot, Nina. Thanks everyone else. Cheers.